It's my real pleasure to introduce Dr. Venkat Srinivasan, who is a staff scientist for the Energy Storage Group at Lawrence Berkeley National Laboratory and the Deputy Director of Research for the Joint Center for Energy Storage Research, or JCESR, the big battery hub. Venkat has been at LBL for
10 years.
10
I have
years.
a pin that came to me recently. 10 years.
10 years. Well, but then you were at Berkeley before that.
Yeah,
right.
as a postdoc for a few years. They don't give me a pin for that one.
Right. Okay. So he's been at Berkeley as long as I can remember because we overlapped. And I'll tell just a personal story to introduce him. When I was a graduate student at Berkeley, I wasn't in chemical engineering. I was in material science, which was chemical engineering light. And I would hang around the Newman Group seminar to try to understand what was happening. And there was an important part every week where we would go and get pretty mediocre pizza just outside of the campus at this place called Laval's, which was unexceptional in every way, except they had cheap beer. But this was the most important part of the seminar for me because it was when I would ask Venkat what the hell just happened and explain to me why the paper we just read was important. So Venkat has an unbelievable ability to explain complexities of batteries in really clean language without dumbing it down. So without further ado, Venkat, we look forward to a great talk. Thank you.
Thank you for the really nice introduction. When people say they're going to tell a personal story, I always worry. I'm not sure exactly what they're going to say. So it's a pleasure being here. I was telling people that I've been here before, not here, but at Princeton. That was many years ago when I came as a visitor. My cousin was a postdoc somewhere here. So it's good to be back, I guess, to some extent, except I don't remember anything from the last time. So my name is Venkat. I work on batteries. And what I thought I'll do today, in talking to people during the day, I kind of realized that there were some people who understand batteries quite a bit. And so for those of you who are in that quite a bit category, this probably will be a bit of an overview on the things that you already know. But I hope to tell you a few things about what is happening in the battery world that hopefully you'll appreciate. But I also realize a lot of people who don't know a whole lot about what is happening in storage, but may be very interested in what is happening. So I thought I'll spend some time sort of walking you through 4 things. First, I'll spend some time talking about the status of battery technology. And I'm going to focus on electric vehicles. I'll say a little bit about plugins, but I'll talk mostly about electric vehicles. And about grid storage. Those are the 2 big things I'll be talking about today. Okay. There have been some recent changes in the last couple of years that make batteries very interesting. And I'll sort of talk about that, spend some time talking about why those changes have happened, what that means, and what else do we have to do to get everybody driving an electric car. So that'll be kind of the goal of this presentation. How do you get everybody driving an electric car? And to get every one of you to buy a battery pack in your home, where your home is powered by solar panels. Okay, so think of that as the kind of the premise of the talk. And I'll sort of walk you through how you go about doing that. And I'll tell you a little bit about what are the research approaches people have been taking, both in container batteries. These are batteries like lithium batteries that are in a box to some extent. And what are called flow batteries, which some of you are working on here, where you have liquids flowing into a cell and sort of holding them in tanks. And I'll sort of talk about that, explain that in a bit. A big problem in batteries is, if you have an innovation in the lab today, it can take you 10 years to reach the marketplace. And I'll sort of touch upon that. Hopefully you'll appreciate the complexity of energy storage as I go through the presentation. But a big challenge that we all have to think about is the fact that time frames and things like batteries and other energy technologies or chemistry technologies can be very, very long. So we have to think about the fact that we have urgent problems in the world today, but may take a long time for us to come up with innovations that can be marketable to the outside world. And how do we think about that is something that I think I'll sort of leave you with in this presentation. And I thought I'll sort of start with some interesting sort of anecdotes so that you all remind yourself about why energy storage is important. I come from Silicon Valley. People all think that I'm not doing my job because Moore's law is the only law they remember, which is not really a law, but hey, that's the only law they remember. And Moore's law says that things double every 18 months. And so they all want to know what's happening in batteries. Nothing seems to be changing. And I kind of remind people that, we had things that looked like this many, many years ago. And the reason we have things that look like this today is because we invented a lithium-ion battery and because those batteries got better. It's easy to forget that, but it is an important part of what has changed in the last 20 years in the energy storage landscape is things that have become smaller, lighter, more energy dense, and that's why we're able to do the kinds of things we're doing today. This disruption that has happened in consumer electronics is slowly beginning to move to cars. I remember maybe even 10 years ago, people saying EVs were like golf carts, right? They go from 0 to 60 in 13, 14 seconds. Who would want to drive them? And today we don't have that debate, right? We know these cars do very well. We still have problems with them. We can't afford them, or they don't have the range that we want. And we sort of talk about that in a bit. But we do see these cars. I saw a Tesla here today when I was walking. In my daily commute, I've got a pretty long commute in California. I don't even count Teslas anymore. There are so many Teslas on the roads, right? And that's kind of interesting. It also tells you that the Bay Area can have a lot of money in it, I guess. But I think the reality is that this is happening, right? We are seeing things on the ground. People are driving these cars. And this morning, I got a ride from Emily in her electric e-Golf. And so it's kind of great to be able to sort of do these things and experience them and get, I guess, pants on the seats, I guess. It's the same idea will start happening on the grid. We're starting to see this. Some of you probably don't know what this is. A very large flow battery installation out of this place called Turlock in California by a company that is making this large iron chrome flow battery. It's like one of the largest installations of iron chrome in the world. You guys might have seen the announcement that Tesla was going to come up with these Powerwall batteries, and SolarCity was going to start selling them. The funny joke that everybody was making is that was the first time that people wanted to take a picture in front of a battery when Tesla announced the Powerwall. So they're doing something that hopefully will become real and something we can all appreciate. California has obviously been leading the charge on this, and they have this mandate called they want to sort of call out for buying electric storage. I was meeting with Rob Sokolov, and we were having a long discussion on how this is not well structured. But irrespective, this is showing the governments are getting involved and trying to move energy storage more towards the market by saying, hey, let's procure them. Let's put demonstration projects out there, and let's learn from them. So it's happening in consumer electronics. It's already happened. It's happening in vehicles. And we think it's going to happen in the grid sector very, very soon. Okay? That's the exciting part of energy storage. So let's sort of switch gears and sort of talk a little bit about history of batteries, right? So here is energy density, very important number if you're driving a car. So the more energy dense you have, the greater the driving range would be before you have to recharge the batteries. Years, okay? We've all running with lead acid batteries for a long time. All of a sudden, a small jump happened. We moved to nickel metal hydride batteries. After that, we've been moving to lithium-ion batteries, and the commercialization that happened led us to increase energy density at approximately 5% a year. That's the improvement in energy density that typically happens in the battery world. It's approximately 5-6% a year. That's kind of the Moore's law for batteries to a large extent, right? But it's a very slow pace, right? This is not the Moore's law we typically think about in semiconductors. It's a very difficult process. And again, hopefully today you'll appreciate why it's difficult, just because, again, the complexity of chemistry as opposed to kind of moving electrons, I guess, is a little bit easier than moving ions and electrons together. So that's the first thing that you should be aware of. But batteries are improving, right? That's the good news about all of this. Similarly, the cost of batteries, which you could argue is more important than energy, because ultimately you're buying a commoditized product, which is energy, so how much does it cost is very important, is also coming down, right? So these are cost of cell phone, laptop batteries, very small cells. In dollars per kilowatt hour, how much does it cost per energy that you're trying to hold in it? And these costs have been coming down pretty dramatically, kind of tapering out somewhere in the 2012, 2013. After this, it hasn't come down that much. It's been hovering in this range. Again, this is all happening because of the consumer electronics industry, right? As we start buying more cell phones and more laptops, there's been manufacturing scale that's kicked in that world, and more batteries are being made. Economies of scale are giving us lower cost batteries, right? That's what is happening here. There was a famous paper that came out last year that sort of looked at the same thing for sort of larger packs, right? Battery packs. So remember now that, let me take Tesla as an example. Tesla takes these very small batteries, these 18650 cells. They take 8,000 of them and they make a battery pack with them. You can obviously do them in a different form factor, but that's what they're doing. They're making a battery pack that's probably this high and this wide from these very small devices, right? That's what they're trying to do. So these are the costs of those battery packs. So remember now the cells are becoming cheaper because of mass manufacturing for consumer electronics. These are for battery packs. And these costs, again, are starting to come down slowly over the last 5-10 years, where we're starting to see them penetrate into the marketplace ever so slowly. This is the good news. Energy is going up, cost is coming down across the world. Right? So let me sort of summarize all of this by showing you what I think is kind of a master plot for vehicles, and then I'll show you grid also on the same plot. What I'm plotting here is the system level dollars per kilowatt hour. So you're buying a full battery pack that you're going to put into your car, like the Chevy Volt or something. How much does it cost? Very important number. And how much volume is it going to take? So more than weight, volume is the most important entity in a car. You could imagine that, in Chevy Volt, for example, the battery sits in the middle, takes away the back seat, the center back seat. And that's a problem. People want the center back seat, right? two very important metrics for electric vehicles. Okay. This is where lithium-ion is kind of today, ballpark, in terms of energy density and in terms of cost, right? Somewhere in the 600 to 400, that range, somewhere in this range. Okay, that's where it stands. What happened some years ago is the Department of Energy started saying, let me start thinking very carefully about how much energy do I really need and how much cost do I really can the consumer really pay for these batteries? So they went through an exercise, and sort of the way they did this was, there's a paper that came out. What they did this said was the engine equivalent, which would be the battery pack, has to cost some amount of money. The rest of the components, the wheels, the brakes, the seats, and all of that will be the rest of the cost. And you've got to have cost parity between the EV and a small mid-size sedan, like a Ford Focus or something like that. That's the comparison they were making. If you go 200 miles, the numbers we came up with were somewhere here. It's $125 a kilowatt hour and somewhere in the order of 500 watt-hours per liter. That's the number that they need. So you can see the gap analysis. This is where we are. This is where we need to be for a 200-mile EV. Okay. Again, the 200-mile, people think is a sweet spot. It's not 100 miles where people worry about range anxiety. The thinking is 200 miles opens up the door for a lot of people to start buying these cars. That's the number. Again, it's a small car. Some of you will be wondering, Tesla actually goes more than 200 miles. How come their energy density is not all the way here? And that's because Tesla is making a large car. It's a very big car. So they're putting a lot of battery to get the range. Downside of that, you're paying for a lot of battery, right? That's why that car costs an arm and a leg, right? So that's because you're just paying for all that battery. So this is the Department of Energy target for what they want battery people to shoot for. Now you can look at this and say, that's great, it's 200 miles, but I really want a car that's going to be like my car that I have today, an internal combustion engine that goes 350 miles. If you do the math on that, it gets a little bit harder. You need a lot more energy, obviously, because you have the same volume of the car. Where do you put the battery? Well, guess what? You got to have a more energetic battery for you to be able to put it there. And so the paper also talks about how you got to be somewhere here, and the cost has to be down here at approximately $83, $85 a kilowatt hour. Kind of the numbers you should be thinking about, 125, 83 kind of numbers. Okay. This is vehicles. Let me talk about the grid for a second, right? That's the exciting new opportunity. We all see solar panels on so many roofs. Can we put a battery pack, right? We see that on the grid, we have stability issues because of the duct curve. Can we put a battery pack? What we're trying to see is there is this whole ecosystem of things that can evolve, right? Remember now, on the grid, it's not obvious the x-axis matters, right? I don't think I care how big the battery is. I've removed the dimension. That's the beauty of it. Now at homes, I'm not sure that you want a chemical plant in your backyard. You may want it to be a very small box, and I can see that. But as we move away from behind the meter, you can start imagining this opens the door a little bit. Today, we are seeing that things like transmission and distribution differential, so think of this as, oh, I don't know, there's a Costco coming up and somewhere in the middle of nowhere. All of a sudden, they need a lot of electricity. A utility company says, I don't want to build a grid there. It's going to take me 10 years to do it. Let me put a battery pack, right? So that's kind of the application there. We're starting to see that batteries are cost competitive. Frequency regulation is another market where batteries are cost competitive today. All the way down to the other extreme, where if you really wanted to have distributed PV, like in your home, and a battery powering it, this can be costing, your battery may have to be in the 50, 60 bucks a kilowatt hour range for it to be LCOE comparable to today's grid electricity in some places, right? Imagine a place like, I don't know, Louisiana or something where cost of electricity is so low, 9 cents a kilowatt hour. How do you beat that with solar and a battery, right? You gotta have really cheap batteries if you get there. So there is this whole range of costs where energy storage in the expensive can start kicking in, but for ultimately getting to everybody to buy a battery for their home, it's going to require us to get down to the kinds of numbers that you start seeing here. So most battery people use a number called $100 a kilowatt hour. That's a good canonical number, because if you can get $100 a kilowatt hour number, we think a lot of exciting things can happen in batteries. Okay? So in many ways, that's the number that people like me try to remember all the time. Let's get to $100 a kilowatt hour, right? So that kind of gives you a framing for where we are and where we need to be. Okay. Now, somewhere around 3 to 5x reduction, depending on the requirements, right? That's kind of the thinking that we all have. This is today. There is a tomorrow, and that looks really exciting. Some of you will remember Tesla making an announcement of a gigafactory. This would be the largest factory. It's bigger than any factory all put together today. Idea here is simple. Let's do what Henry Ford did, right? We'll do two things. We'll do vertical integration, so let's not bring in materials, let's try to build it ourselves, and let vertically integrate all the way. Second thing we'll do is we'll exploit economies of scale. Learning curves kick in, all sorts of wonderful things kick in. This is going to dramatically change the way costing of batteries happen in the next 5 years? What's happened is that in the last 2 to 3 years, it's not just Tesla talking about this. All the big companies are all starting to think about ramping up production volumes and starting to reduce cost of batteries. So if you kind of go back and look at this figure here, remember I showed you it's coming down, what looks like it's happening is something that happened to solar approximately 10 years ago, right? All of a sudden, solar 10 years ago, there was a dramatic manufacturing boom that happened in China. And guess what happened? Prices of solar panels started plummeting like a brick. $1 a watt used to be the goal, and today we are less than $1 a watt in terms of solar panels, right? There is a feeling that maybe what I call the solar effect is starting to come into batteries, where large manufacturing scales are kicking in across these big companies that are in the battery space, where they're going to drive down cost dramatically, and in the next 5 years, we're going to see a sort of a dramatic cost reduction that's going to happen in batteries. Okay? That's the big change that has been happening in the battery world. I'll try to quantify that again by going back to this plot. Remember now this plot just tells you here's where we are today in terms of energy and cost, the targets, and this is the target for the grid where you don't care for the x-axis, you only care for the y-axis. The feeling is that by 2020, this number is a little bit undefined only because we don't know when these factories will come on board and how long the factories will take to get through depreciation and all of that. It looks like we'll be approaching somewhere in this range where the costs are going to be down below $200 a kilowatt hour. Remember again, I told you $100 is the magic number. It looks like we'll be below $200 a kilowatt hour sometime after 5 years. Energy density is also increasing, and this is happening because of some chemistry changes we'll talk about in just a bit. Dramatic changes, right? Really exciting. But there are some innovations that we need, and those innovations have to come into play. It's not just going to be about manufacturing scale. It turns out there are going to be innovations in chemistry. That is something we'll talk about today. That's the first thing that needs to happen. The second thing that needs to happen, obviously, is we got to go beyond that, right? We've got to still drive down to $100 a kilowatt hour. For grids, you got to go even lower, and you got to get the energy density up this way, right? This is where I think we have to have a very nuanced view on this solar effect that I'm talking about. I don't believe that solar panels and batteries are very similar. Solar is a pretty mature technology. Crystalline silicon is pretty mature. Battery technology has a lot of problems in it. It's not a technology where you can just plug and play. You can just buy a battery and dump it onto the grid, or mix and match a bunch of different battery company products and put them on the grid. There are some really, really interesting differences between those two. And a big question that I ask myself is, as you start thinking about making larger and larger grid devices, do you really want a lithium-ion battery? Is that the best battery pack for you? And we sort of talk about that. I'm one of those who believes that you need to have a diversity of technologies, a diverse portfolio that allows you to start exploiting this idea that I have multiple things that I want to do in the world with batteries. I want to drive cars. I want to use them in my backyard. I want to do frequency regulation. I want to think about day to night storage, and I want to think about 3 days of range storage so that I can use it, right? I want to do all of that with storage. Right? How do you think about that, and what technologies do you need? The second thing is, how do you go from here to here? What are those technologies? What is the status of those technologies? And then I'll talk about how do we bring them to market and how soon it might take to do that. This is going to be the outline of my talk. I'll sort of walk you through this whole roadmap, at least in my perspective, a roadmap of how do you go through this innovation. What are the bottlenecks? And give you a sense of how difficult it is in some cases, and how some things could be very easy, right? You might be sitting in the audience thinking, I can do that, right? So that's kind of the purpose of this presentation. Let me also sort of tell you something that I said in the previous slide. It's not just about energy and cost, right? Those are the two things that I focused on because it's an easy way to tell a story. In the end of the day, there are these other axes that go into this thing. If you take electric cars, can I charge fast? That's going to happen very soon, right? All of us will be wanting to charge in 5 minutes. How do you think about that? Can I use this for 15 years, which is what we typically use our gasoline cars for, right? Today's batteries, we think will last 8 years, maybe 10 years, maybe, right? How do you get to 15, right? These are all very important issues, and I sort of talk about the various things that are happening. In this case, I've tried to tell you where we are in battery technology compared to where we need to be. The red tells you where we are in these different metrics. The blue tells you where we need to be, and I'm doing it for plug-in hybrids, which is a much easier goal. The feeling we have is that in the next 5 years, plug-in hybrids will start becoming more and more ubiquitous. This is like the Chevy Volt system, which has a gasoline engine and a battery pack. Cost of batteries will come down where we can start thinking about these as becoming cost-effective. Electric cars have a bigger challenge. We've got to think about them very, very hard. Again, the blue means that this is the target. Red means that you are some percentage of the target, in this case 40%, or in this case it's 60%. And you can see that except for cycle life, where we think we can do fairly well, we can't do the other things that we want to do. Right now, we're all focused on cost. As an industry, as an academic institutions in national labs, But the minute we start thinking cost is going to come down, every other thing is going to become very important. Again, the reason why I think we have to have a diversity of thinking, right? This is not like a crystalline silicon solar cell where we kind of know a lot about it and all we have to do is get the cost down. There's going to be a lot more that needs to happen from an innovation perspective. The grid is a lot more complicated. And I wanted to show this plot that the Energy Storage Association sort of collected some years ago. The x-axis tells you how much power is required, and the y-axis tells you how long the battery will be used, right? So it's called the discharge time. You can do things which, like frequency regulation, where all you're doing is taking away the pulses that are existing in the electric lines, and you don't need a whole lot of movement of energy in those cases. The times are very short, all the way up there where you're doing things like storage across a whole commodity market, or you're doing things like the consumer energy management, where you're sort of moving energy from one side to the other over many periods. And so in this particular case, you can be off in days, right? Sitting there and thinking, I got to store energy over a full day. So all across a map in terms of how long we want to store energy, what is not obvious is lithium-ion is the best thing to do across this very long spectrum from seconds to hours, right? It seems like we should be having other technologies that come into play. We need to have incredible safety, and it's not obvious that we have the answer with us. So that was kind of the premise of how I want to sort of take this presentation with you, is this idea that we need to have a diversity of how we think about batteries as we go forward. Let me just quickly tell you where the costs are. This is the cost model that came out. Let me just say something about cost. It's pretty much impossible to find costs of batteries. Everybody has costing, and you can't believe any of them, right? So I took it out of a study that I thought was fairly decent. We've done some work ourselves as part of the Battery Hub, where we looked at cost very, very carefully, and so I sort of believe the things that we all did, I guess. So you can argue with that. So the battery itself has some manufacturing cost to it, some pack costs, and some of it is materials. If you kind of break it down a little bit more, cathodes tend to be kind of expensive, and this can depend on the cathode. I've picked a particular cathode that tends to be a little bit cheaper. If you have a more expensive cathode that has cobalt in it, this can be a dominating cost. The separator is the next one, and the electrolyte is the third. Those are the three fractions. And in manufacturing, you have a few different processes that are sort of expensive. What's happening today is people are focusing a lot on this thing here. They're saying, let me cut this cost down so that I can take away this fraction as much as I can. Obviously, it's very important for us to start saying, okay, I've started working on this fraction. How do I take care of that fraction? How do I think about how do I get the cost down? And again, remember, it's not just about cost, right? There are other metrics there. So sort of the idea behind what everybody's trying to do is very simple. Then you go back to this graph and you say, okay, I want to decrease dollars per kilowatt hour. I can either decrease the numerator, meaning I take cheaper materials, lower cost manufacturing, packs that are made in a much easier fashion. I can get the cost down. The second thing I can do is I can increase the denominator. Take the same material, and if you double the energy, you cut the cost down by half, right? Very simple way of thinking about it, right? That's a big fraction of what many of us do. So let's do a battery 101, right? Let's talk about how are we going to do this. How are we going to find a way to increase energy density, get the cost down, get safety in, get the charge times, do all the things that I told you about. Okay. There are fundamentally only 4 ways you can store energy, right? I call this my simplest graph because batteries are actually very simple, except it's very complex. The first thing you could do is you could take an electrode, put it in solution, and you form a double layer, right? If you do that, you form what is called a double layer capacitor. So the capacitors are basically double layers that are forming at an electrode-electrode interface. Very simple, high surface area. The ions can move very, very fast. All you're doing is moving it across a Debye length. That's like 20 nanometers. So very quick, right? You can boom, charge and discharge these things. There is no dimensional change. Nothing is moving much. There is nothing that is intercalating. These things can last years. You can give it to your children if you wanted to, right? These will last tens of thousands of cycles. It's wonderful. Problem is, there's not much energy in these things. All you could do is take the surface area and form a double layer on it. Not much is happening in the bulk. And there's only so much surface area you can get in a material, right? So this is limited by energy, great for power, great for life. Okay? The next logical thing you can do is you can say, well, I really want to get some bulk storage going. So what I'm going to do is I'm going to take that ion, in this case lithium, put it into the lattice and move it into the lattice, right? This is called intercalation. This is what all the lithium batteries do. They take lithium, put it into graphite on one side, they take it out of the cobalt oxide or the manganese oxide or whatever on the other side. This is what we do. This is great because you're taking advantage of the bulk of the material, so you can increase the energy density. The downside is the lithium moves in. There's only so much lithium you can put in. After that, it packs it up, right? And when you put too much lithium into it, the volume has to expand. And bad things happen. When volume expands, there are stresses created, there are cracks that form, and bad things can happen, right? So reasonably good for energy, can last a long time, but if you try to push the limits, bad things can happen with it. You can now say, well, I don't want to be constrained by this space of the lattice space that I have and the number of lattice sites that I have to intercalate. why don't I do something a little different? And I call this a dissolution precipitation mechanism. You could call it plating, conversion. There are various terms you could use for it. Think of it as lithium comes in or copper comes in and plates on an electrode. And then the copper just becomes a little bit thicker. You plate some more, it becomes a little thicker, right? So you can keep building this layer continuously, forever actually, if you wanted to, with this kind of a mechanism. The downside of this is the electrode is changing shape all the time. Every time you charge and discharge the battery, the metal is dissolving, the metal is coming back. And you see this in lead acid batteries, you see this in zinc electrodes, where you have to sort of think about controlling it. So great for energy, many times, not always, but can be very poor when it comes to cycle life because, again, you're changing the dimensionality. And the big challenge there is how do you control the dimensionality as you make those changes. The last thing you can do is you can say, well, I don't want to do any of these things. I'm going to take a molecule, a liquid, react it, and convert it to a different molecule, a reactant and a product. Both in the liquid phase, I could do gas phase if I wanted to. This is called a flow battery. The easiest way you could think about a flow battery is to put it in tanks, store the chemical in a tank, flow it into a cell, react it, convert it from a reactant to a product, and put it back to another tank. That's what we do in a flow battery device, right? Here, we don't have dimensional changes. All we do is change the form of that liquid or the gas from one form to the other, and we store the reactants and the products in separate tanks outside of the cell somewhere. Basically, batteries are one of these four things, right? You can mix and match them. People have tried to take a capacitor electrode, pair it with this, and they call it a hybrid capacitor. They've tried matching this and this together. One side will be an intercalation electrode, the other side will be a deposition electrode. They've tried taking these particles and flowing them. They've tried taking these things and not flowing them. So essentially, you're trying these variations on this theme of trying to make sure that you can get to an innovation which involves something in these four things. And at the end of the day, the mechanism that is dictated the energy storage is going to be dependent on the charge of the materials that you picked, right? Depending on it. If you pick lithium, you're going to see this mechanism. If you picked a cobalt oxide, you're going to get that mechanism, right? It all depends on which way you're playing this game. Very simple in my mind. And we've been doing this game for many years, right? Since the days of the lead acid battery. And if you kind of go back, the old batteries, we used to have lead on one side, lead oxide on the other, sulfuric acid in the middle. We made a lead acid battery. We then moved to saying, let's take nickel hydroxide and cadmium. With potassium hydroxide, we made a nickel cadmium battery, right? The thing is, in these batteries, everything is fixed. I fix the anode, I fix the cathode, I fix the electrolyte in between. Everything is fixed. I gotta switch that. Everything is fixed. I have nothing to change, really. This whole concept of playing a game with batteries, finding new things, all happened when we moved to lithium ion. Lithium ion is a platform chemistry. That's the first thing people have to recognize. It's not one single anode, cathode, electrolyte material. It's actually a family of anodes, cathodes, and electrolytes. All we're doing is we're saying lithium moves from one side to the other. That's why we call it a lithium ion. We don't define where it's moving from, where it's moving to, and what it's moving through. We don't define any of those things. And depending on the materials that I pick, I can see very different batteries showing up. Here are the materials people are playing with today. Some of them are commercial. Some of them we hope will become commercial in the future. They're all very, very different from each other. Just to give you an example, the battery in your cell phone is actually not the same battery that's in your Tesla. It won't be the same battery that's in your Powerwall, and it's not the same battery that's in your Chevy Volt, which is kind of interesting, right? All of them are lithium-ion batteries, but they're actually not the same. And the failure modes are kind of completely different depending on what you picked. Therefore, I think of them as very separate batteries, even though we call all of them lithium batteries. The beauty of the chemistry is that I can find more things in these three boxes. And when I find more things, hopefully they're better in some metric. They're more energy, or charge faster, or give me longer life. Therefore, I have a way to sort of tweak the chemistry for the application that I've chosen for myself, right? That's the diversity and the beauty of lithium-ion batteries. It gives you a chance to sort of find those beautiful things, right? And I get excited about that because I feel like this gives us a chance to have innovation as we go forward and meet the kinds of metrics we were talking about in the beginning of this talk. If you kind of go back to this picture here, where I showed you that lithium-ion came in and is improving, what we're seeing in the last few years is these new materials are starting to come into play. Before this, all we were doing was engineering. And the feeling is that engineering can help us some more, maybe 30% increase in energy density is possible. The rest of it will have to come from materials. We have to find new materials that get us more energy, lower the cost, and do all the things we need to do. So I'll now give you a second tutorial, which I again say is a very simple slide that you have to, the only slide you need to know if you want to work on batteries, right? And I'm going to do that by taking a lithium-ion battery as an example. What I'm plotting here is the voltage of the battery on one side, and the amount of lithium the material is going to hold. In the bottom, I'm showing you for a material carbon, on the top for cobalt oxide. The more I go to the right, I can hold more lithiums, which means I'm holding more electrons per gram per volume. That's very important. The more I can hold, the more energy I can get from the battery. The y-axis is very important because the difference between this potential and that potential is the voltage of the battery. And the more the voltage, the more the energy. Energy is the product of those two things, the product of the capacity, meaning the x-axis, and the difference between these two on the y-axis. Okay? So it's very simple. What we want to do in batteries is either expand the x-axis, you got to put a lot more electrons to get stored in the same weight or volume, or you've got to move this voltage up or that voltage down. That's all you got to do, right? It's very simple. This is what every battery person is trying to do, right? When they think about energy storage, that's all they're trying to do. If you go too low, here's the first problem that shows up. Instead of the lithium going into the carbon, it starts to plate and forms lithium plating reactions. This is one of the reasons why batteries go up in flames when you try to fast charge them. It's because instead of intercalating, which is the reaction that you want, you plate lithium, it forms dendrites that shorts through the cell and you get a fire. Right? So that's the first big thing nature stops you from doing. You can't keep pushing down the voltage too low because this reaction comes into play. You can't go too high in voltage either because the minute you go past this limit, you start to oxidize the electrolyte. So remember now that these batteries have to have a thermodynamic limit to them. For those of you who've thought about water-based systems, water electrolysis is the defining reaction that you have to always think about. At 1.2 volts, oxygen comes out in water, hydrogen comes out on the other end. Similarly, for these non-aqueous systems, we've got to think about the oxidation-reduction reactions. At approximately 4.3, the electrolyte starts to oxidize, which means that even though I have a lot of capacity in this battery, I can only use half of it because the rest of it is happening at a potential where I can access it. That's the problem with it, right? If I go to those potentials, bad things happen to the battery. The cycle life goes down pretty dramatically. I can't use them for the 15, 20 years that I want to use them, right? That's the second thing that happens. Now, I could try to move the capacity, try to store a lot of ions in the material. The problem you get into is that you have these reactions where you start to form what is called the solid electrolyte interface reaction that occurs in these chemistries, an electrolyte reduction reaction. This forms a passive layer on the surface called an SCI, and for battery people, this is a very important thing because this dictates the life of the batteries. It's a layer we understand very little about. We don't know exactly what the composition is, but it controls a lot of what happens to the battery life. So again, if you want to get to 25 years, you've got to learn to control this reaction. The last thing you've got to think about is that as the electrode is charging and discharging, it's breathing. The volumes are expanding and contracting. And when that happens, it starts to create stresses. You have fatigue, you have failure, you have breakup, all those bad things happen. Right? So you've got to think about that also. At the end of the day, the game we are playing is this game, right? We're thinking about how do you increase that voltage up, how do you decrease that voltage down, how do you deal with the stresses, how do you deal with this reaction, how do you push the capacity without actually getting any of these products out. That's kind of the game we're all playing. And some of them do it using cathodes, some of them doing it using anodes, some of them doing it using electrolytes. But you can use the same idea to kind of think about battery research in a more holistic fashion, not just lithium batteries. So the first thing we're doing, this is the roadmap slide I was telling you about, right? If you look at the industry today and the academia and the national labs, all of us are focused on trying to increase the voltage, which means that we've got to understand all those reactions that are happening at the surface of the cathode and try to figure out how to move those potentials higher. That's the first big thing that is happening. This will all happen in the next 5 years. That's the hope. There are some innovations that need to happen. There are breakthroughs that need to happen. I don't want to schedule the breakthrough, but the hope is that in the next 5 years, you'll be seeing innovations that lead us there. The second thing that needs to happen is that we've got to move away from these carbon materials to things that have a lot more capacity, things like silicon and tin anodes. And you're starting to see the beginnings of that in the market, but there's a lot more research that is still going on that we hope can come into play. Next, what's going to happen is that we're starting to think about taking this reaction where lithium plates, which I just told you is a bad thing, we want to take that lemon and make lemonade from it by saying, let's remove the graphite and just put lithium as the anode material. It's something that we've been trying to do for 30 years. It feels like we have the tools and techniques and understanding now to revisit that problem. The reason we want to do that is it has 10 times the capacity. Now remember, capacity doesn't mean energy, but it gives you a chance to get maybe 40 to 50% higher energy than today's batteries. Cut the cost down by maybe 40 to 50% compared to where we are today, right? Compared to lithium-ion batteries, which is kind of remarkable if you kind of think about it. Another thing that happens when you move to these metal anodes is that you can start getting into cathodes that have very high capacity. Today we get 140 to 180. You can get up to things like 1600. Again, the idea being that it exploits the advantage of having lithium metal where you can get cathodes that don't have lithium in them and try to put them into the frame. So this is in the lithium-ion world. Let me kind of expand that a little bit more. You don't have to use lithium there. you can start to think about using other things, right? So there are people, for example, in J. Caesar, and people here who've been thinking about using magnesium instead of using lithium. Again, the idea is simple. Magnesium has a charge of +2, lithium has a charge of +1. Why not take advantage of the second? It's something you can do. You can start saying, well, this is all great, but it's all lithium-based. I don't want to go to a non-aqueous system because electrolytes can be very expensive. Turns out one of the biggest problems with lithium-ion is that everywhere across the spectrum, you can introduce moisture and other impurities, but moisture is a big problem, which means we got to have dry rooms during manufacturing, and that can be expensive, right? You've got to be very careful about the material choice because guess what? You can expose it to air. Lead-acid batteries can be made in really, really dirty conditions because it's all water-based. There's something beautiful about using water-based systems. They're very forgiving, and the manufacturing can be very simple. You know, in India, I'm from India. In India, there are places where you could go, and literally these are small shops, where they would remove the sulfated plates in a car battery and put a new plate in and give it back to you. It's that low-tech in terms of being able to manage that way. Really sort of fantastic way of doing it if you have an aqueous system. So there are people, including people here, who are saying, well, I don't know if I really want to be going the lithium route at the expense that is there. I'm going to start thinking about low-cost materials, maybe using sodium ion, maybe going aqueous because of that, and maybe I just want to go back and use protons, right? Well, what's wrong with protons? Especially if you're going after grid storage where cost becomes more competitive and not energy density. There is a feeling that we can use this to our advantage by going after things that don't necessarily have to have lithium in them. So the kind of the diversity of the various things that people have been trying to do. And the idea here is that each approach has a promise here, right? You can increase energy density in some cases, decrease the cost in some cases, right? So it gives you sort of the diversity of the kinds of things that you could do with it, right? That's the beautiful thing about what is happening here. So let's kind of walk through that. What I'm going to do in the first part is I'm going to sort of tell you a little bit about how we are going to the first stage, what are the challenges there, and I'm going to give you a couple of examples on how you're going to do that. And I'm going to do that by talking about high voltage cathodes. Again, the big problem here, like I just told you, is that you are here at this potential, and if you want to increase the potential even higher, the electrolyte oxidation reaction becomes a very important reaction. What is happening is there is a feeling that we have to do two things. One is that we have to find new electrolytes, completely different from the ones we're using today, where you can expand that window. Think of it as sort of not taking water anymore, but going to non-aqueous. Similarly, can you go to a different non-aqueous chemistry that has even higher potential compared to the ones before? The second thing is playing the game of kinetics. One of the things that looks very promising is the idea of coating the material so that the electrolyte and the electrode are not seeing each other. There is an intermediate layer that is more protective on the surface. This is starting to look very promising and interesting. We're actually starting to see some products coming out that actually take advantage of this. It's still not very long life. That still has to happen. But I think that's where research comes in, the understanding that comes from research allows you to start thinking about how do you control this reaction so that you can start thinking about exactly how to get this reaction to occur, right? So that's the first thing that is happening, is a way for us to start moving towards getting to these high energy chemistries. The second thing that is happening is that we want to move towards what we call alloy anodes. These are things like silicon. I told you about that just a little while ago. The big problem here is that as you put lithium into silicon, the lithium has to go somewhere. When I tell you things like it's got 10 times more lithium capacity in it, well, the lithium has to go somewhere. And the way it does it, it expands the silicon particles. By approximately 300%, the particles break and they crack and they fall apart. There have been a couple of approaches to this, one of them using nanotechnology to make things like nanotubes that have been looking promising. One big problem here is scale-up costs and whether we can really make it at a large scale. That tends to be an issue. The second thing that is happening is that people are using these things like conductive binders, ways in which you can sort of hold these particles together, even if they break, sort of still get connections to them so they don't isolate. We've been thinking about how you could take that approach. This is looking promising. What I'm showing you here is the capacity versus cycle number. The capacity is slowly fading, but not as dramatically. And I'm also showing what is called Coulombic efficiency. Coulombic efficiency is how efficient is the reaction going back and forth. You charge and discharge the battery, and how many lithiums are you losing. Every lithium that you lose is cycle life, just so you're all aware. And what you're seeing here is that if you really want to get 3,000 cycles from these things, the efficiency has to be 99.992%. And if you kind of look at the scale here, 99.992 looks a lot like 100, and you can see that these batteries aren't quite at 100, right? So there is still a problem in these chemistries. Comes down to the interface. We were having this conversation this morning about the importance of interfaces in batteries. It is the single most important thing when it comes to cycle life. One has to think hard about what is happening on the surface of these materials, what are the reactions, how do you control them? This is a big area of research that is happening. If we can get there, then we can certainly get this to happen. So these two are the near term. We are moving towards high voltage. We hope we can get there. We are moving towards silicon. Right now, we are mixing silicon with graphite, our existing anode material, mixing them together in different ratios. Hopefully, in the next 5 years, we'll have more and more silicon, less graphite. Okay? That's what we're doing today. And that is going to get us to this energy density here. The cost is going to come down because of the big companies doing manufacturing. The energy is going to go up because of these innovations. The question is, how do we go there? How do we continue to cut the cost down for grid storage? How do we continue to go to the right of this diagram for the energy density? There are chemistries that look really exciting when you kind of look at that. Here is lithium ion today, and what I'm plotting here is the theoretical energy density. These are not practical because they're not practical systems yet. Lithium ion is practical, but the energy density is somewhere here from a theory perspective. Everybody's excited about lithium sulfur because the energy density is significantly higher. There was a lot of excitement about lithium air. It has its own set of challenges, but the energy density can be an order of magnitude more than today's systems, at least from a theoretical perspective. This is kind of the excitement plot, right? There is something there for us to do when it comes to electric cars. We actually can get high energy system. And remember now, energy and cost are connected. High energy means could be low cost, right? So there's a lot of excitement around that. The commonality, if you forget zinc for a second, which actually people like Dan are working on, is that you have to get lithium metal to work. That's the commonality among these two things, right? If you can get lithium metal to work, there is a feeling that can open the doors to a variety of things. So if you kind of look at the roadmap again, the first step is high voltage and silicon. That's 1 and 2, 2 or 1, depending on how you count. The third one looks like we've got to find a way to make lithium metal happen. If we can make that happen, then I think a lot of exciting, interesting things open up immediately. So for lithium metal, the biggest problem, like I was telling you before, is that when you plate lithium onto these anode materials, they don't plate uniformly. They actually plate in these dendritic structures. And the dendrites go through the cell, shot through the separator, and get to the other side, and then you have problems. You know, many of you who have an old watch battery, not the Apple Watch, but the older watch batteries, they all have a lithium metal anode. And you will notice that it probably says, do not charge. There is a reason. That's because this happens. And then you get a fire, right? That's why they say, do not charge those batteries. This is an old problem. People have been looking to solve this problem for 30 years. It turns out, before lithium ion came out, people were trying to make this battery commercial. They couldn't. That's when they said, remove the lithium, throw it away, let's get graphite in and make a commercial battery. That's what Sony did, which is an amazing innovation, right? Now we're talking about moving back to lithium metal, partly because we understand the world a lot better today, partly because we may be forced to go solve the problems in old chemistry that we haven't been able to solve before, right? That's part of what happens in these things. There are a couple of approaches. One of them that's coming out of Berkeley is where we've been using block copolymers. One of my friends there, Natasha Balsara, has been pioneering this idea that you can take a very stiff polymeric block, stop the dendrites from growing. Think of it as putting like a concrete wall next to a tree root and stopping it from literally going through. But then you got to feed the tree. In this case, you got to send the lithiums through. So he's got a second block that allows the lithium to go through it. So he's using a block polymer idea to do that. He's seeing a lot of success with it. We'll see if it ends up becoming something that can be commercialized at room temperature. The big problem there is it's a high temperature system. The second approach is to use ceramics. These have gained a lot of traction recently. You may be hearing the word solid state. It's the latest buzzword in batteries. Everybody talks about solid state batteries. This is really what they're talking about. They're talking about, instead of taking a liquid electrolyte, taking a solid, either a polymer or a ceramic, putting it against lithium metal. That's where the excitement comes in. In my opinion, and I'm happy to be proven wrong because of innovation, that's the beauty of innovation. In my opinion, these are longer term. And I'll tell you why in a second, but these are longer term. This is not in the next 5 years, right? I believe these are 10, 15 years down the line. Actually, maybe 15, 20 years down the line, right? These are difficult challenges, and I'll talk about why I believe that it's a long time frame for us to see them as a real product. But really, there's some excitement stuff going on here in lithium metal, but it comes down to this. I've been spending all my time talking about lithium. Let me sort of switch gears and talk a little bit in the last 10 minutes about flow batteries and sort of wrap it up. So if you kind of look at the graph I showed you before about the grid, what I told you was there is a diversity of times of discharge that are important. Everything from seconds all the way to many hours and maybe to days that are important. If you kind of look at the cost of a battery, in this case a lithium battery, versus the time, it's kind of expensive at very low cost. It turns out balance of plant, things like current collector and materials are all very expensive at the left of the diagram. As you go to very high discharge times, the cost kind of levels off for a lithium battery. What if I don't do that, but I go to something called a flow battery? A flow battery is kind of a simple idea, right? It's a lot like your gasoline engine. You've got a gas tank, you move the gas to your internal combustion engine, you react it, you power your car, you throw away the products. Instead, what if you capture the product, store it in a different tank, and then you bring it back when you have to charge this again, right? So discharge is going from one tank through the cell, charge is going to the second tank and bringing it back to the cell and using the energy from the sun to charge it up again. It's a very simple idea. What you're doing is you're separating energy and power. The energy is in the tank, the power is in the cell. Think of it as I have a bigger gasoline tank to go longer range for the same 4-cylinder engine, or I can take the same tank and go to a V8 and get all the power I need with the same sort of the tank size that I had, right? So you can kind of separate energy and power to some extent in these systems, right? That's the beauty of it. Because I can separate energy and power, I can take a very large tank, which means that I'm going more to the right of this diagram, and I can start to cut the cost down if I can get low-cost molecules. So if you look at a flow battery cost model, these are techno-economic models of the flow battery, you can get to lower cost on lithium-ion battery and forget all these different nomenclatures in terms of what we're doing there. But really the main message of this plot is that if lithium batteries kind of saturate in cost somewhere here, and this number can go down as we have more innovation that I was talking about, flow batteries can actually cross over at long discharge times. But you've got to be long in discharge time. You've got to be in the 4, 6, 8-hour range for it to be cost effective. If you only want to store energy here, you cannot use a flow battery today. But if you want to use energy for a very long time, think of diurnal storage, then flow batteries start to make economic sense. Right? So what do we need to do in a flow battery? There are 2 parts to this. The first part is these chemicals that are in the tanks have to be very high energy density. That's kind of important because the tanks cost money. And if you have a huge tank, it's going to cost you money. With the higher the energy density, I can put the tanks very small because I don't need a whole lot of the tank to store the molecules that I have. That's very important. The second thing is if I have a very corrosive molecule, then the tank can be expensive because you got to do things like Teflon lining and very expensive things, and you don't want to do that. The second thing I got to do is that I have to go to that cell that is in the middle. Now the cell can be a very expensive affair because sometimes these chemicals don't want to react very quickly, so you've got catalyst in them, and that can be things like platinum that are expensive. All of these things have membranes in them, and the membranes can be very expensive. So when you have a big flow battery cell, you're putting a lot of catalyst and a lot of membrane, and that can be very expensive. So you want to minimize the size of the cell as much as you possibly can, which means that these materials have to be very high in power. They have to kind of quickly charge and discharge. And they have to do that very reversibly so that you get long cycle life. If they form side reactions and bad products, then the cycle life won't be very good. That's the second big requirement. The third and important thing is you've got 2 liquids flowing next to each other. They want to mix through this membrane. So you've got to find a way to stop that membrane from letting the mixing to happen. That low crossover can be a killer for most flow batteries. It can be one of the most fundamental issues that flow batteries face. So you got to think about that very carefully. Today, we've been playing the game of using these kinds of materials, vanadium, zinc, hydrogen, chromium, things like that is what we've been playing with. Some halogens in some cases, metals in other cases is what we've been playing with. I think we have to start thinking about what do we do for the next 7 to 10 years. Some of these materials are looking very, very promising, partly because what we're able to do is we're able to take the fuel cell expertise. A flow battery looks a lot like a fuel cell, and you can start applying those kinds of ideas and knowledge onto a flow battery that you've been doing in the fuel cell world. And that's actually yielded a lot of results in the last 5 years. And that'll continue. But as you start looking into the future, I think there is also a lot of games being played where people are saying, well, let me cut the tank size down dramatically by looking at high voltage systems where we can use redox organic molecules, things that are operating in a non-aqueous space, or starting to think about tuned aqueous molecules, molecules that are not something you pick off the shelf, but you're tuning them, you're making them, you're synthesizing them. They're aqueous, so they can be cheap, hopefully, in the way you put them together, but they have more tailored attributes to them where you're able to sort of get a higher voltage or get better reversibility, things that you couldn't do if you're just picking something off the shelf, right? There's been a lot of movement towards that and trying to think about ways in which you can control all of these reactions. So I think as we go forward, we're going to see a lot more innovations happening both in the lithium-ion world and in the flow battery world. And the lithium-ion innovations in the contained thing are going to start slowly going towards non-aqueous, aqueous systems, things like proton conducting, sodium conducting materials, where the whole manufacturing scale I was talking about is slowly starting to come down to even those areas. So what I'll do now is I'll sort of finish off by summarizing a couple of things. I just told you a variety of things people are doing. I didn't cover everything that was happening in the battery space. I gave you a snapshot of that. Now I'll sort of summarize the energy density increase or the cost reduction you can get compared to today's technologies for both vehicles and the grid. It's sort of a map that I made up, and you can argue with me as to whether these things should go up or down a little bit here. And I'll sort of talk about time in just a second, and left or right. So these are the sort of the next generation, next 5 years sort of a time frame, incremental things that are happening. I don't want to use the word incremental lightly. These are very important, difficult challenges here, but they'll hopefully have an impact in the next 5 to 10 years. But we're also doing things that are longer term in the picture. I've been very careful. I've not defined the x-axis for you. It's unlabeled for a reason. And the reason it's unlabeled is because one of the big challenges that I think all of us have to think about is that chemistry is hard, as I alluded to. And the question we have to ask ourselves is how long will these innovations that are more lab innovations actually take to reach the marketplace, right? If you really are saying, I got to have the electric grid stabilized, I got to take out of the duck curve, how long will it take to do that, right? Turns out if you go to the history of batteries and look at it, and I'm going to do that by taking 3 material innovations that happened in lithium-ion batteries, because every other battery chemistry is going to look even worse. Cobalt oxide was the first one that was kind of discovered in the world. That took 11 years for Sony to make a battery with it. Okay, that's kind of the time frame it took them. Well, you could argue first time was the hardest. The second one we tried to do with lithium manganese oxide, and that took 23 years, right? So you could argue with me that maybe the second one is the hardest. Turns out the most successful story was the third one, the lithium iron phosphate one. They were actually able to go from lab to market in, I want to say, 3 years or 4 years. They actually had a contract with Black & Decker. A123 was the company that contracted Black & Decker. And they're able to leverage all those years of learning that happened. Manufacturing learning, how do you think about packaging, how do you make devices with them, how do you think about testing them fast. They were able to leverage all of that, and they were able to do that. Ultimately, they tried to go after the vehicle market, which is really what I'm plotting, sort of thinking about here. And they were able to do that in 9 years' time frame. Right? Ultimately, they got into vehicles somewhere in the time frame of 9 years. I sort of look at this graph and I average the time from lab to market in batteries as being approximately 10 years. But there are some lessons I think that we can learn from all of the historical ones. Lab to market is a very slow process, right? Historically, I think in materials, the number that people use is 18, right? In batteries, you would argue it's the same thing, right? It's just hard to do these things. And part of it is a problem with scale-up and manufacturing. It is a challenge, and we sort of saw this in A123. There are sort of studies that have looked at A123 scale-up and the problems they had doing that, where something that works very well in the lab, and all of you recognize this, right? Oftentimes you do 5 experiments on the same material, a couple of them work, 3 of them don't, and you can publish a paper, and it's great. But you can't have 1 out of 10 experiments working in the real world, right? Yield of 10% is just don't even start making a company, right? You can forget it. Yields have to be 90% plus for you to actually sort of have a company that's profitable, right? That's a big challenge, right? And part of this is very simple. As you start scaling up, guess what? Defects matter, impurities matter, the surfaces matter, the anode talks to the cathode. Well, guess what? That matters. And especially in this chemistry here, that's what happened. The manganese dissolved on the cathode. It then migrated to the anode and started killing the anode. Well, you won't know that if you're doing some lab scale studies where you're not worrying about a full battery that has an anode and a cathode, right? Those are the significant challenges we have to think about very closely. I think that what we need is a close connection between R&D and manufacturing and industry. If you have it disconnected the way we have it today, it's going to take a long time for us to move technology from lab to market. It'll take more than 10 years, I think. And ultimately, right, we have to think about market demand. One of the problems A123 got to was they had a battery and they were searching for an application to some extent. They were kind of jumping around trying to find the application. They were a little soon for the grid market. They kind of didn't time it very well. I think we have to think hard about what are the problems from the world's perspective and think about what battery do we need to invent. Today, we're seeing a trend where it feels that lithium ion is going to solve everything for us, right? Just because it's there, it's present, the cost is coming down. I, for one, am not convinced that's the answer. And I think if we don't look, that's what we're going to find out. We're going to find out there's no market demand for the product we have, right? And so I think it's important for us to kind of think about the diversity of things we want to do, because that's the only way to have a big success. Let me not plug, well, let me not. Let me plug for a second. So we have a meeting in November, in November 3rd. It's called the Bay Area Battery Summit. What we did in the summit was very simple. It was at Lawrence Berkeley. We said, okay, we always do technology conferences all the time. There's one coming up in a few months that I'm the chairman for. But the battery is a lot more than technology. It's going to be about the policies. Think about the graph I showed you, the gap analysis, right? Think about incentives to try to get that gap to work, right? How do you get people driving cars and buying batteries at a time when it's still expensive, right? You got to think about that angle. And ultimately, it'll come down to the market. I've been really worried about the solar effect for batteries, right? Because I think it's a wrong trend because there are still some problems to solve. How do you think about the market when you have innovations? How do you bring them to market? We discussed all of those. There's going to be a white paper that's going to come out. These are the authors. Danny and Julie are from the solar world. They sort of saw the world of solar. He was the founder of Sanjavedi, and she was the senior vice president at SunPower. Ted works for a startup battery company that's literally trying to do behind the meter battery leasing. It's solar, that's what happened, that took off. Solar took off because of solar leasing. He wants to do that in batteries. George Crabtree is my boss in the Energy Storage Hub. So the two of us thinking about technology. Bart was the founder and CTO of A123. So he sort of literally saw the story of how do you take a lab to market and why the market can sometimes come back to kill you, right? So he sort of saw the whole transition. So writing a white paper based on this, it's going to come out very soon. We're going to be talking about 8 recommendations of things we think are critically important for us going forward. I'll kind of stop with that by sort of quickly summarizing the 4 things I told you, which is, hey, battery costs are coming down, so the world is going to be really exciting. If you're in the market for an electric car, wait, it's going to get really cheap. You may have to wait a little longer before you buy a battery for the grid, but hey, it's going to happen one day, I think, if you continue to go down this path. I sort of summarized the various sort of the status of the technologies, and I then told you there were a variety of options, both in lithium-ion flow batteries and in non-lithium-ion, where hopefully we're trying to make an impact. And the last thing I told you was it takes a long time for these things to actually reach the marketplace, and it's something that we have to think about. I'll stop with that and take any questions that you guys might have.
That's fascinating, but it seems to me that you've neglected the infrastructure, the gas station equivalent,
Absolutely.
and somehow there's a cost associated with that that must influence the choice you make.
So you're absolutely right. One has to think about charging. Workplace charging has become a big issue. The cost modeling for the grid actually takes into consideration a couple of things. One is the inverter. The second is the installation. You're hiring somebody to come and do these things. And there's permitting cost. Funny stories about permitting. In California, this is behind-the-meter storage is evolving as we speak, where permitting cost in one location apparently can be $250 for a behind-the-meter storage. In another place, in the Bay Area, can be $2,500. Right, so this is an active area where we don't know how the costs are going to manifest itself. Very important topic, and I absolutely agree with you. I didn't kind of talk about it and touch upon it, but I was focusing more on the battery chemistry side. Very important topic.
Hi, nice talk. I just have a very quick question. So on your on one slide, you show a hexagon where at each corner you label the goal and yeah, right. So I noticed that one goal is that you want to have a fast discharge to 80% of that depth of discharge DOD in 15 minutes. I'm just wondering. Why is 80%? Why is it not fully discharged? Is it just an industry criteria?
It's an industry criteria. So that particular graph came out of the targets came out of the United States Advanced Battery Consortium, which is the Ford, GM, Chrysler, and their view on how they want to use it. It turns out if you're doing discharge, your power, you still have to accelerate even though you're at 80%, if that makes any sense, right? If the car is down at any state of charge, if somebody presses the accelerator, they want the acceleration to happen and they want to do that, so that's part of it. On charging, the criteria is set in this way, right? You want to at least charge the battery enough that the person can continue to drive. And you want to have a fast charge code that sort of says, I'm going to push enough charge that you can get home, right? This has happened to many electric car owners where they're somewhere in the middle of nowhere. They got to get home. They don't have enough juice. Can I spend 10, 15 minutes, plug in something, get 20, 30 miles and go home? So that's kind of the scenario they're playing.
Hi, Professor. Thank you for your excellent speech. I also have a question that, there's some batteries for the mobile phones, mobile machines, and there's the battery for the electrical cars, and there may be other batteries for other things, like robots. Is there any difference between them? Maybe we use this battery is not suitable. It's suitable for the mobile things, but not suitable for the robots. Is there any we should classify it, or we should focus on which batteries we can do best and we can extract their potential? Thank you.
A good battery is one that is specifically sort of designed for the application you're going after. I do not know a whole lot about the robots. I assume is like the Roomba. I don't even know if they use lithium-ion. The last time I checked, mine had a nickel metal hydride, which is remarkable in its own right. But let me sort of then compare. I'll compare the two things that I know very well. Consumer electronics, mobile phones, watches, and cars. Both use lithium batteries, but both are different chemistries. So the mobile phones typically use cobalt oxide as a cathode. And right now in some of these phones, you're starting to see silicon graphite blended anodes. For electric cars, you use pure graphite anodes. and you have some sort of a layer or a spinel material as a cathode. You don't use cobalt oxide because cobalt is expensive. On the grid, you will see a wider variation where people are more worried about safety and life, so they're trying to do other things. I showed you the flow battery. There's a few more installations like that. We are seeing a few more installations of aqueous-based systems. We are seeing a lot of lithium-ion systems also, but we're seeing more diversity there. I do not, the drone market tends to be a lot like the consumer electronics market. Part of the reason is cycle life is an important criteria, right? Your cell phone lasts a couple of years, and then you're gonna get a new one anyway, so you don't care about life. A car has to last 8 years. A drone can last 6 months, I guess. It all depends on how you want to think about these things and where you pick the battery. The big markets, which is where everybody's driving towards, is either consumer electronics, vehicles, or grid. So it's not obvious that a drone market is that big at this moment.
So as you move towards, the new chemistries, the new materials, how much of the learning that's gone on in manufacturing can be transferred to, silicon, sulfur, magnesium, stuff like that?
So let's take some simple ones. Magnesium, in principle, might look a lot like lithium-ion battery. So in principle, you could argue plugging it in, fitting it in. It's great. Is lithium metal? Let's forget the reason metal for a second. Lithium metal will look the same? It's not obvious. Now we have a material that is not going to be put in the same way. Do I take these roles? Do I do the whole thing in some sort of a incredibly nitrogen-free atmosphere? Not obvious. That's going to be the same. Flow batteries are not manufactured, right? They're assembled to a large extent, which is completely different. Right? A lot depends on how these chemistries end up, right? Some of them will work better than others. But it's going to require totally different changes across the board as we go forward.
Is there, so you mentioned a desire to have sort of R&D closer to manufacturing in terms of, development. Is there funding specifically towards, studying the manufacturing from, a more scientific, level?
There's some. Obviously, as you can imagine, right, the battery companies over years have iterated and got to something. The Department of Energy is the one that sort of thinks about this problem very carefully, saying, I don't want to go through the 5-year learning cycle every time I change something. Let me think about the science behind it. So there is a little bit of stuff that is happening that allows us to start going towards that direction. I think part of it is there has to be, you have to learn the industry problem threat to really be relevant about it. So I think that's where the close connection becomes very, very important. One of the things that I used to do before was I used to take that, you may remember this graph that I had, vehicle batteries and grid batteries and dynamic axes. I used to take a plot, and for personal curiosity, I plotted that to ask myself, if you were to take a decision, so the way I do research is simple, right? My own research group, that's some incremental stuff on the left of the diagram, and some on the top. That's what we all do, actually, have a diverse portfolio. I said, if you were not taking a decision based on risk of technology, but if you took a decision based on manufacturing needs, how would you do it, right? And there's a beautiful map that shows up about some that are difficult and some that are easy. Again, it's my view of how this is. I assume that if you guys don't think about that, right, you will have your own view on which of these would be easy to decide. Yes, sir.
Do you see any future for nickel-cadmium batteries? I know in the past they've somewhat been written off because they have poor memories, but with advanced battery management technologies, you can technically shock them and kind of re-erase that memory impairment. So is there any potential future for these guys?
So, cadmium has the toxicity issue, right? That's really one of the reasons why it's sort of been going away. It's not just the fact that there's a memory problem in it. Could you solve memory? I don't know. Yeah, there are these memory busters. I'm not one of those who believes it actually works. It's a hard challenge, right? It has this mechanism called the dissolution precipitation where there is a shape change that happens in these chemicals, crystallization that happens. And some of it comes from that. Turns out the nickel electrode also has a memory in there, and that hasn't been quite solved. And the structural change that happens. And, you may be able to control it, but one of the issues you have to think about is there a market demand for those chemistries? Nickel metal hydride is kind of an expensive chemistry. Metal hydride can be expensive, nickel is expensive. So it's not obvious that those are the two materials. I'm one of those who actually fundamentally believes that you can have enormous innovations in aqueous systems, where I think the new knowledge can come in that we've used in lithium batteries is finding cathodes and anodes that don't look like nickel hydroxide and cadmium hydroxide, but look different, that are catered for the protons to go in and out, or for some other ion to go in and out. There, I think there could be some interesting things to find.
Thank you very much.
So when you consider the flow batteries, I didn't see you include fuel cell electrolyzer combinations in that case.
Right.
Have you discounted that possibility?
I haven't. Obviously, people are looking at it. I mean, one of the things that I worry about quite a bit is the efficiency, overall molecular efficiency with doing electrolysis, hydrogen storage, right? Many of efficiency is cost at the end of the day to some extent, right? So I think 70–80% is what everybody wants to see. And so there are people pushing on that. Reversible fuel cells have been around for a while. I was thinking about excluding all this, I think of it as a flow battery.
Hi, here. I have a question about the silicon anode. So you said that there's a company which who make a mix with 5% of silicon with graphite. But for silicon anode, the capacity is only like saying like 3 to 10 times bigger than graphite, but the expansion is 300 times. And I guess you said that also the cycle life for the battery that they're making is only like 300 cycles. But usually for lithium batteries, it's about like 2,000, which means that, like in total, the amount of the capacity increase is like if you look at the overall lifetime, the total energy it can deliver is much smaller than the lithium batteries. Could you please share some comments on that?
Right. So first of all, the only market where silicon graphite composites are entering is the cell phone market. It is not anywhere else. But really, the cycle life is 200 cycles. Nobody cares beyond that. Right? If you go to an OEM cell phone company, they typically last for a couple of hundred cycles. Right? If you can get 200 cycles, then they have okay. That's the first thing I'll say. So in that particular case, that's always required. The advantage from an energy density is trivially better, because the amount of silicon in is trivially more. Right? So it's not that high. But the way the battery industry views these things is they don't want to en masse this one interesting thing in the battery industry. They'll never go to a new material if they can help it. Right? Because they'll add a little bit over the next 10 years. They'll sort of move towards a new thing. Like nickel. I remember this example. Lithium nickel oxide. In the 90s, we knew it was working. Everybody wanted to go away from cobalt. Nickel was a bit cheaper commodity price-wise. People are thinking we should move to that.
Okay,
They never adopted it. It took them years, right, to get it in there. Right? Because they just didn't want to get there. Right? So that's really what's happening. Is this longer-term trajectory of how they want to use this.
Do you have any concern with the supply of lithium if with the growth of its usage with more batteries?
Right, so we looked at that some time ago. If all of a sudden tomorrow all of us are driving lithium-based vehicles and buying their homes, there is no lithium for it, because there is no great ramp up. But I think if you were willing to, assuming that doesn't happen and there's a slow increase in demand, from an overall demand perspective for vehicles, there's enough lithium to go. At some point, we may have to start recycling the lithium, but for I think the next foreseeable future, lithium is not the problem, it looks like. It's only going to be a flow problem, meaning I can't ramp up very quickly, but it's not obvious that the market is going to happen quickly. Maybe in the long term, we will, obviously at some point, if everybody is driving an electric car and it's all based on lithium, then we'll have to start with recycling and things like that for sure. But it is a problem only if you get to that scale of everybody doing that. Before that, it doesn't look like huge.
Well, I'll ask a question, as is my right. So, Venkat, with, Minnie asked a really good question about utilization, and when you look at the Ragone plot now, systems are far lower than what cells can do, even when you factor in the mass for safety and cycle life concerns. So from your perspective, are we going to get to a point, and just for everyone in the audience, depth of discharge is a very fuzzy number based on specifications. As Venkat showed, you can go to much higher utilizations and get far fewer cycles for a given material in a given system. So on that cost curve, how much of it is materials innovation and how much of it is better utilization of existing materials to get to that point?
That's a great question, right? I think today we're sort of assuming that there's a 70% or something utilization that we want to get. Let's think about an LCOE on the grid, right? It's two things, right? It's not just about utilizing more of it, which I think is important, and people have to think about that more, and that's going to involve getting to those high potentials and understanding the reactions. But if I can also double the life, it just changes the economics like dramatically in one shot, right? So I actually believe there has to be a lot of effort in thinking about how to use what we have really well and use it for however long we possibly can to push it, because that can be a dramatic decrease in cost also. Absolutely.
But you think that, you know, going to silicon or going to lithium air, is there, and you smile, but is there a point where it just becomes Sisyphusian because systematically such a battery, if it were to exist, is simply too dangerous to utilize fully?
Oh, I see. I don't know the answer to the question, right? I mean, obviously, the whole game in batteries is to be able to control the energy that you have in whatever fashion. It gets harder and harder the more energy you're storing in it, because now you're controlling a bigger and bigger storage device that has a lot of energy in it. I will say that things like lithium air, when you start thinking about high energy systems, you may have to spend a lot of weight, volume, and cost on all of those things, right? And so then, does it really pan out? Is a really an interesting question, which I don't know if we know the answer to until we start playing the game to figure it out, right? I mean, you know, the flow battery guys rightfully argue that it's a much safer system.
Yep.
Because I can close the two valves, and the tanks can be very far away, and the two energetic materials don't see each other. And that's a great argument for how this could be a lower system cost level, right? So I think one has to have a more nuanced view of how we think about these things. That's why I kind of worry about, hey, there's a rapid decrease in cost of lithium batteries, just use that, right? So not fresh.
Well, there's a reception, so we can ask him more questions, and thanks so much for a great talk.
Thank you so much.